Nuclear Fusion in the Sun by Nick Andrews and Jack Forster.
The Sun is 75% hydrogen and 25% helium. The energy released from the Sun results from nuclear fusion. It occurs when nuclei combine to produce a nucleus of greater mass. In this case, hydrogen nuclei or protons fuse to make helium nuclei. Here is an explanation of how the energy is released. These represent 4 hydrogen atoms, or protons. The gravity from the Sun's core pulls them together, and then the positrons, the apples, help transform 2 of the protons into neutrons.
The reaction is complete. The positrons are no longer needed and are ejected, creating a lot of energy. Yeah!
Oh, Lord! Do it again.
In order for the reaction to occur, the temperature needs to be extremely high, 40 million degrees Celsius to be exact. The surface of the Sun is too cool for the reaction to occur, but the core isn't. The Sun has 3 main parts: the connective zone, the radiative zone, and the core. The core, or the center of the Sun, takes up 25% of the Sun and is hot enough for this reaction to occur. This is why the reaction happens in the core, creating 85% of the Sun's energy.
That is how nuclear fusion in the Sun works. Thanks for watching.
The Sun. It is a unique, clean and infinite source of free power, delivering more than 1,000 kilowatt-hours per 1 square meter. 1,000 kilowatt-hours is the amount of energy found in 100 liters of heating oil. Wouldn't it be wonderful if we could use the energy from the Sun? Solar energy, wind power and water energy are forms of very clean energy generation that can be converted to, for example, light. Photovoltaic systems use solar cells to convert solar energy into electrical energy. Solar cells are usually made of silicon, that is a semiconductor material, which means that it can conduct electricity under some conditions but not others. When looking at the periodic table, we see that silicon is part of group 14 and is situated between aluminum and phosphorus. That being the case, a silicon atom has 2 electrons in its first shell. It has 8 electrons in the second shell, but it has only 4 electrons in its outer shell. The outermost electrons are called valence electrons and are of utmost importance because all silicon atoms consist of not more than 4 valence electrons. However, all of the silicon atoms will form bonds by sharing electrons to achieve a full outer shell with 8 electrons, which makes them very stable. In order to disturb the stable state, doping atoms are purposely inserted into the silicon. When boron is combined with silicon, free holes will be created because boron has only 3 electrons in its outer level. With 5 valence electrons, phosphorus creates additional free electrons. And that's where the magic happens. A solar cell consists of two silicon panels sandwiched together. One layer is doped with N-type dopants, the other is doped with P-type dopants. To allow an electrical flow of electrons, a front and a back contact are installed to the layers. Glass is installed on top of it to protect the layers and the electrical contacts from damage. Now it's time to take a closer look at the area between both layers. In the N-doped semiconductor, there is an axis of electrons. In the P-doped semiconductor, we observe positively charged electron holes. The electrons in one layer will find their corresponding free holes in the other layer. Consequently, an internal electrical field builds up at this transition that does not permit electrons and holes to jump into the other layer. However, if photons hit the silicon layers, electron-hole pairs will be created. If this happens in the electrical field, electrons are moved to the N-doped layer and holes are moved to the P-doped layer. The system will fall into a state of imbalance because of an excess of electrons in the N-doped layer. The corresponding holes can be found in the P-doped layer. It goes without saying that these free electrons and free holes try to combine. However, the electrical field does not allow such a condition. But if you connect the top layer to the other layer, for example by using a cable, you will see that electrons are traveling to the free holes. This flow is called an electrical current and can, for example, light a lamp. Solar panels can be installed on the ground or on your roof. The solar cells collect the rays of the sun and convert solar radiation into direct current, which is eventually converted into more usable alternating current by a piece of equipment called an inverter. Connected to the inverter is another device that is going to measure the electricity produced by the photovoltaic system. Generated electricity may then be reimbursed by your electricity supplier.
Solar cells convert sunlight directly into electricity. We start with sand, which is processed into highly purified silicon. In a process called doping, trace amounts of special impurities are added to this purified silicon. For example, when silicon is doped with boron, the resultant material is called P-type. When silicon is doped with phosphorus, the resultant material is called N-type. When pure silicon is doped with both boron and phosphorus in just the right way, a p-n junction is formed. This process establishes a permanent electric field in the crystal. When a p-n junction is made so that light can strike its top surface and metal conductors are attached to the p and n-type sides, a solar cell is formed. When sunlight strikes the solar cells, electrons are ejected from the atoms and the permanent electric field in the junction steers them to the n-type side. If a wire is connecting both sides of the solar cell, electric current can flow whenever sunlight is striking the solar cell.
Many homeowners have heard about solar energy and are interested in solar energy, and this is what's called a photovoltaic system. Photovoltaic indicating that the sunlight is converted directly to electricity through these what's called PV, photovoltaic panels. And this is a demonstration system that would, in effect, showcase all the different parts associated with a system that a homeowner might want to investigate for his home. What we'd like to start with is solar panels, photovoltaic panels, which we have here, and these are oriented towards the sun to capture the sun's energy. That energy is created by the sun and is transferred through the panels into electrical energy, so we have an energy transformation going on there. That energy comes down through some wires, and we have some various parts here, including disconnects, fuses, circuit breaker boxes that are important, because we always want to be within codes and standards, National Electrical Code being an important consideration. We always want to do things safe by codes and standards. Here we have what's called a charge controller, which is a device that is common if you're using batteries. If you're having batteries as battery backup, we want a charge controller so that we can control the level of charge in the battery and also the level of discharge. Through that we go to a disconnect, a switch, and then we have in here we have our batteries. These are what's called deep cycle batteries, which are special batteries for deep charging and discharging. Regular old car batteries are not going to work for us. So these are an important concept if we're using batteries in our system. From there, we go to what's called an inverter. And an inverter takes the DC, what's called direct current, which is supplied from the batteries, from the panels, so it's DC form of energy, and it converts it to AC, alternating currents, which is in the form that most homes appliances use. They use AC electricity. We go through a typical disconnect, which is generally fused. It's an on-off switch. Okay? From there, we go to a distribution center, your fuse box. Most houses will have one of these that have your breaker boxes in it. So here I have two breakers that distribute the power to various parts of my simulated home. One is this light here, which is just a very simple 60-watt light bulb, and the other is distributed to this AC outlet. So I can take any typical home appliance, a hair dryer, a phone charger, a computer, plug it in, and it would work just the same as if you plugged it into your house. Okay? If I want, I can also use the energy direct from the DC, direct from the panels, or directly from the batteries to power what's called DC devices. For example, this light is a 12-volt DC light, and it runs off of the batteries direct without being converted into your typical home AC power. So most of the components here you would find in your home if you decided to go with photovoltaic system. And this demonstrates on a small scale the basic components and the basic techniques, including metering, so we get information. Okay? We know how much energy we're getting, the currents, the voltages, how much energy we're using, and we can use that to determine charges in the battery and lifetimes and things like that.
The preceding was a production of New Mexico State University. The views and opinions in this program are those of the author and do not necessarily represent the views and opinions of the NMSU Board of Regents.
Before we move on, I want to clarify something that I've inadvertently done. I think I was not exact with some of the terminology I used. So I want to highlight the difference between two things that I've used almost interchangeably up to this point, but now that we are about to embark on learning what voltage is, I think it's important that I highlight the difference, because initially this can be very confusing. I remember when I first learned this, I found I often mixed up these words and didn't quite understand why there was a difference. So the two words are electrical, or sometimes you'll just say electric instead of electrical. So electric potential energy and electric potential. And I think even in the last video I used these almost interchangeably, and I shouldn't have. I really should have always used electrical or electric potential energy. And what's the difference? Electrical potential energy is associated with a charge. It's associated with a particle that has some charge. Only that particle can have energy. Electrical potential or electric potential, this is associated with a position. So for example, if I have a charge and I know that if it's at some point with a given electric potential, I can figure out the electric potential energy at that point by just multiplying actually this value by the charge. Let me give you some examples. Let's say that I have an infinite uniformly charged plate so that we don't have to do calculus. We can have a uniform electric field. let's say that this is the plate. I'm going to make it vertical just so we get a little bit of change of pace. And let's say it's positively charged. Positively charged plate. And let's say that the electric field, it's constant, right? It's constant, no matter what point we pick. These field lines these field vectors should all be the same length because the electric field does not change in magnitude. It's pushing out because we assume when we draw field lines that we're using a test charge with a positive charge, so it's pushing outward. So if I wanted to ask you, let's say I have a 1 coulomb charge. Actually, let me make it 2 coulombs just to hit a point home. Say I have a 2 coulomb charge right here. 2 coulombs, and it's positive. A positive 2 coulomb charge, and it starts off, I don't know, let's say it starts off at 3 meters away, and I want to bring it in 2 meters. I want to bring it in 2 meters, so it's 1 meter away. So what is the electric or electrical potential energy difference between the particle at this point and at this point? Well, the electrical potential energy difference is the amount of work, as we've learned in the previous 2 videos, is the amount of work we need to apply to this particle to take it from here to here. So how much work do we have to apply? Well, we have to apply a force. We have to apply a force that exactly, we assume that maybe this is already moving with a constant velocity, or maybe we have to start with a slightly higher force just to get it moving. But we have to apply a force that's exactly opposite the force provided by by Coulomb's law, right? The electrostatic force. And so what is that force we're going to have to apply? Well, we actually have to know what the electric field is, which I have not told you yet. I just realized, as you can tell. So let's say all of these electric field lines, I don't know, let's say they are 3 newtons per coulomb. So at any point, what is the force being exerted from this field onto this particle? Well, the force from the electrostatic force on this particle is equal to the electric field times the charge, which is equal to, I just defined the electric field as being 3 newtons per coulomb, times 2 coulombs, it equals 6 newtons. So at any point, the electric field is pushing this way, 6 newtons. So in order to push the particle this way, I have to completely offset that, and I actually have to get it moving initially. I know I keep saying that. I just want to make that point, hit that point home. So I have to apply a force of 6 newtons in the leftward direction, and have to apply it for 2 meters to get the point here. So the total work is equal to 6 newtons times 2 meters, which is equal to 12 newton meters, or 12 joules. So we could say that the electrical potential energy, and energy is always joules, the electrical potential energy difference between this point and this point is 12 joules. Or another way to say it is this, and which one has a higher potential? Well, this one does, right? Because at this point, we're closer to the thing that's trying to repel it. So if we were to just let go, it would start accelerating in this direction, and a lot of that energy would be converted to kinetic energy by we get to this point, right? So we could also say that the electric potential energy at this point right here is 12 joules higher than the electric potential energy at this point. Now that's potential energy. What is electric potential? Well, electric potential tells us essentially how much work is necessary per unit of charge, right? This was electric potential energy was just how much total work is needed to move it from here to here. Electric potential says per unit charge, how much work does it take to move any charge per unit charge from here to here. Well, in our example we just did, the total work to move it from here to here was 12 joules. But how much work did it take to move it from there to there per charge? Well, work per charge is equal to 12 joules per what? What was the charge that we moved? Well, it was 2 coulombs. Well, it equals 6 joules per coulomb. That is the electric potential difference between this point and this point. So what's the distinction? Electric potential energy was associated with a particle. How much energy, how much more energy did the particle have here than here? When we say electric potential, because we essentially divide by the size of the particle, it essentially is independent of the size of the particle. It actually just depends on our position. So electric potential, we're just saying how much more potential, irrespective of the charge we're using, does this position have relative to this position. And this electric potential, that's just another way of saying voltage. Voltage. And the unit for voltage is volts. So 6 joules per coulomb, that's the same thing as 6 volts. And so if we think of the analogy to gravitation, we said gravitational potential energy was mgh, right? This was force, this was distance, right? Electric potential is essentially the amount of gravitation. If we extend the analogy, the amount of gravitational potential energy per mass, right? So if we wanted a quick way of knowing what the gravitational potential is at any point without having to care about the mass, well, we would divide by the mass, and it would be the acceleration of gravity times height. Ignore that if it confused you. So what is useful about voltage? It tells us regardless of how small or big, or actually positive or negative a charge is, what the difference in potential energy would be if we're at 2 different points. So electric potential, we're comparing points in space. Electric potential energy, we're comparing charges at points in space. Hopefully I didn't confuse you. In the next video, we'll actually do a couple of problems where we figure out the electric potential difference, or the voltage difference, between 2 points in space as opposed to a charge at 2 different points in space. I will see you in the next video.
In the next 4 minutes, I'm going to reveal a crazy revenge story of how I and 56,743 other folks, just like you, reduced our electric bill up to 75% and more in just 60 days. In fact, many of my friends, neighbors, and customers have completely eliminated their electric bill forever. That's right, we pay 0 to the electric company. And now you can become part of this exclusive group too. I'm going to show you how to quickly and easily produce free, 100% green electricity 7 days a week and break free from big energy for the rest of your life. But let me ask you, are you fed up paying through the nose each month for overpriced electricity? Are you disgusted being chained to the big utility monster to get your power? Do your eyes pop out of your head each month when you open your electric bill? My name is Michael Harvey, and I know exactly how you feel, because that's how I felt watching a good portion of my paycheck being siphoned off each month just to heat or cool my house, or to cook on my electric stove. It was like a fat hose was attached from my bank account directly to the power company. Every 30 days, you could hear a loud sucking noise, the sound of my hard-earned money being drained from my account. They had me by the throat, and being an electrician by trade, it was a double whammy. It felt like they were squeezing the life out of me. And that didn't sit right. Being dependent on any big-wig company for the bare-bone basics in life gnawed at me like a bear caught in a trap. I knew I had to do something. So 4 years ago, I was desperate to reduce my ever-increasing and skyrocketing electric bills. I changed all my light bulbs to energy-efficient ones. I unplugged all my stuff from the walls when I wasn't using them. TV, stereo, lights, clock. I even went without air conditioning on scorching summer days. And I live in California, so you can imagine how blazing hot the sun is in July. To say the least, my wife and kids, sweating and dripping in the heat, plugging and unplugging every cord every day, weren't too thrilled with their energy maniac husband and dad. After all was said and done, I managed to save, get this, a measly $16 off my electric bill. Woohoo! Strike up the band. My family disowned me. My valiant, environmentally conscious efforts to conserve energy and save $16 bought me a month of sweat-stained clothes and overheated, grumpy kids. I was furious. Not with my wife and kids, but with the electric company and my dependency on them. I knew I had to find another solution because simply trying to conserve energy doesn't work. What happened next changed my life.
Suppose you wanted to move a large log. That would take energy. Where could you get the energy to do it? One place, of course, is from your own muscles. You could supply the energy to push the log. Or someone else could supply the energy. Then the energy would come from someone else's muscles. Or you could use a machine, like this bulldozer. Then you'd be getting the energy from gasoline. Or you could even use an electric motor. Then the energy to move the log would come from electricity. But let's say you didn't have a friend to help you. And let's say, at least for now, that there weren't any machines around that use gasoline or electricity. Then where could you get the energy to move the log? You could still use your muscles, of course, or the muscles of other animals. But are there still other things around you that might have energy that you could use? Well, here's a small rock. Suppose you wanted to crack it in two. That would take energy. Where could that energy come from? Suppose this happens. The energy to break the rock in two came from the large rock that fell. But wait a minute. There is energy in a rock? How can that be? It doesn't look like there's energy in the rock now. But there was when it fell. What's going on here? The answer is that when the rock was falling, it had a special kind of energy called kinetic energy. All that really means is that it was moving. And because it had kinetic energy, it was able to apply a force to something else by falling on it.